Hello folks, today we are going to see average acceleration. It's when a particle's velocity changes, the particle is said to undergo acceleration or to accelerate. For a motion along an axis, the average acceleration, we write AVGA over a time interval delta t is average acceleration is delta v divided by delta t is v2 minus v1. v2 is final velocity, v1 initial velocity. t2 minus t1, t2 final time minus t1 initial time. The instantaneous acceleration is when we have acceleration with a limit delta t tends to O, it's almost O, and we have dv dt is this notation of calculus. The acceleration of a particle at any instant, the second derivation of its position delta xt with respect to time. So to find the acceleration, we can to derivate we use the second derivation to find the acceleration. We will derivate the xt, we will find the dv, and when we again do the derivation, we find the acceleration. Okay, we will use it and we will see it in the examples here. We need to remember some basic rules of calculus here. Let's go to see the first example. A cyclist starts his morning ride and after 10 seconds his velocity is 7.2 km/h. At that moment, he sees a dog approaching and slows down for 6 seconds until the bicycle stops. Calculate the average acceleration in the first 10 seconds. So in the first 10 seconds, we need to change it to meters per second because we have time in seconds here. So we will use a method called link chain conversion. We have a video here about it, and we write here 7.2 kilometers divided by 1 hour and multiply by 1000 meters divided by 1 kilometer multiplied by 1 hour divided by 3600 seconds. We will cut kilometers with kilometers, hour with hour, and we have just meter for seconds. It's just to multiply and divide it by 3600 seconds. We have 2 meters per second. And we will use the formula here. The average acceleration is v2 minus v1. v2 final velocity is 2. And we have the time interval of 10 seconds, and we find 0.2 meters for squared seconds. Let's go to see the letter B. In the letter B, the braking average acceleration of the bike, because the person is stopping in and use 10 seconds to do it. So we have here O minus 2 because it's deceleration. The final velocity is O and the initial is 2. And we have minus 1 divided by 3 meters for squared seconds. Let's go to see another example now using calculus. A particle's position on the x-axis given by x equal minus 4 minus 27t plus cubic t. We need to find the velocity and the acceleration. We saw that we need to derivate. The first derivation is the velocity and the second derivation is acceleration. Let's go to see some rules about it. We have here dx dt, that it means vt, dx dt is vt. When we have here 4, a number without a letter is O, derivation is O. We bring the power down as a coefficient. We have here 1, we have here down, and reduce the old power by 1, like we see here. decrease the power by 1. Here we see the same thing. Here we bring the power down as a coefficient 3t and reduce the power by 1. So we have here minus 27t O plus 3 72. So we have a power of O and power of 2. All the number or the letter elevated to with power of O is 1, okay? We have minus 27 plus 3 squared t. It is the Vt. Let's go to find the At. Again, the same idea is 0, and we bring the power down as a coefficient and multiply by 3, and we have t2 minus 1. We will decrease the power by 1, and we have At is 60. Okay, we have the exercise here. You need to stop now and try to do the exercise. I will do now the exercise. To do the second part of this exercise, you need to remember a formula that probably you saw in the high school. This is the formula, okay? So if you don't was able to do, you can do now with this formula. Stop now and do. Okay, let's go to C. It's final velocity minus initial velocity. We have a time, and here you use this formula to find delta x. It's the distance. We have h1 meters. Here it's just derivation with the same idea. Stop now and try to do. I will quickly just to show how do it, okay? You can choose stop in any time. Is the same idea. Bring the power down as a coefficient to reduce the old power by 1. Decrease the power by 1. Okay? We have two derivations, and we have here all the derivations here until the final. Okay? Bye bye. Thank you.